All right, well, Brian said this is going to be fun for everyone. I think it's going to be fun for almost everyone. I've been planning on winging it tomorrow, so we're going to do one step below winging it. And so what I did was, I think about 2 weeks ago, I wanted to look at writing a WebSocket server with HTTP4S. I wanted to get experience coding with functional streams. Thank you for that. I just wanted to kind of get my head around the programming model. And I looked out to see what examples were there. And I found a couple. They fell into a couple categories. One category kind of demonstrated the mechanics of WebSockets in HTTP4S, but didn't really show how to do a lot with more than one user at a time. And the other category showed how to do more sophisticated things, but it was based on older versions, usually using the Scala Z streams. And so one of the things that you read online on Twitter occasionally is after you're done stumbling around in the dark, write the blog post that you wish you had found. And in this case, I set out to write the example that I wish I had found when I was trying to learn this stuff. And so what we're going to do is we're going to walk people through it. Now, one thing I'm going to start with here, if people want to see this thing in action, you can go to martinsnyder.net. And oh, well, I'm not connected. The rest of you can do this. You can go to martinsnyder.net, and then on the top right of the navigation, there's a projects list. And there's the chat server is listed there. If you go to that website, you should see a running chat server that you can play with. And the way it's set up is once somebody connects to the chat server, they establish their username, and that's effectively constant for the session. And then the information is going to flow through the WebSocket, and that's just going to be the transient messages that move through the stream. And then we have the state, and the state is going to be which room they are in. So when you send a chat message, it will go to the other people that are in the same room as you, and you can change. Yes? Can you zoom in? Absolutely. Well, yeah, sorry, I hadn't gotten to the, well. Oh, goodness. All right, hang on. Yeah, well, I haven't done this in a while. Control mouse wheel is not doing it. Who's used IDEA recently?
Did you switch out of Directila?
So that's okay. Now we need the. How do I switch the theme?
Settings, file settings. Themes right there on the right.
There was only one other theme. Should we pick that one, or is this good enough? So which one do we like? Sorry. Believe it or not, I've done this with no preparation. Okay, so the way the WebSocket protocol works is an HTTP request comes in and it requests a switch of protocol. And what HTTP4S is going to do is it's going to respond with this WebSocket builder, which will switch the protocol and then bind streams to the information coming up and a separate stream to the information going down. And we want to move the data, take the upstream messages, we want to send them to all of the participants in the room. one of the key concepts when you're dealing with functional streams, every stream is a single entity. It's this linear flow of information. And there's a couple things that we're going to want to do with our chat server that a single stream is not well suited to. One is we're going to want to move things from one stream to another. And the second thing we're going to want to do is we're going to want to project information to multiple streams. And to do that, we're going to need concurrency objects. So this will handle both control flow and moving messages. And the two most important objects that we're going to be using are a queue and a topic. So a queue is the standard, the last in, first out, maneuver for the messages, and then the topic is going to implement a publish subscribe mechanism. Now, where we are right here, this is a HTTP4S router object. And so the pattern there is we do pattern matching on the request coming in, and then we're going to respond with the stream. Now, because we're in the context of a single request here, we can't really create shared objects. And so the things that we're dealing with, the queue and the topic, they need to come into us in the very beginning. And so if we look at our constructor, we'll see that we take a queue of input messages, and we also take a topic of output messages. And I'll show everyone where those are created. But what we want to look at right now is kind of the handshake as it relates to the user WebSocket. So given a stream of messages coming from the output messages from the topic, we can subscribe to that topic, and that gives us a stream. And then we're going to filter out the messages that are not intended for us. So a broadcast message would go to all users. Everything else is designated for individual users. And then we can take that output message and we'll convert it to a string, and we'll send it down. So this is relatively simple from the WebSocket perspective. The topic is publishing the messages, and we are subscribing to them. And once we have an output message, it's a relatively trivial transformation. Sending things from the client into the system is a little more complicated. We're getting text from the users, and what we want to do is we want to take that text and we want to parse it into an input message, and then we're going to enqueue those input messages on the queue. Okay, so give me 1 second here, and we're going to take a look. Hang on. Let me just get out of presentation mode for a second. We'll just take a quick look at the input messages and the output messages to show that to people. Okay, so the output messages, there's going to be 3 kinds. We can have a message that's sent to a single user, a message that's sent to multiple users, and then a keep alive message, which I'll explain at the very end. I'm sorry, the IDEA users, do you know how to switch which file I'm looking at from presentation mode? No. Thank you. The input messages are more complicated, and here's where the parsing logic is. And in this case, we're just writing kind of traditional Scala logic. So I take the line that comes in, and we're just going to split it so that we have 3 strings. The first 2 words delineated by white space, and then the rest of the message. And then we can pattern match against our expected commands. So there's a few other things we do from the WebSocket perspective. So one is when we're getting events from the WebSocket, we can get an event that indicates that the WebSocket has closed, and we're going to change that into an input message that the user is leaving the system. So most of the user messages are going to be things that the strings came from the user over the WebSocket. We parsed it and we projected that forward. But we can also have special messages that we insert on the user's behalf, and this is one example. The other thing here is that before we send things through the queue, we're going to concatenate two streams. We have an entry stream, and then we have this stream of all the parsed input. So we can insert static events into the stream as well. And you see up in the top here, we're adding a special event that the user enters the room. So the way that our stream is going to look from the WebSocket perspective is we have a static event that the user is connecting, and then we have everything that they type and send, and then we'll have a static event that they have disconnected. And this will make the processing of the server logic much simpler, because we kind of have those guarantees. We have these guarantees that all of the user input is going to be bookended by these two separate events, and then we know that everything that's coming back out will go down to the user. So I'd like to pop up a little bit to the top level now, and we'll see how things look from a much higher level of the application. So if people look at the examples for writing HTTP4S applications, they'll see this block down here is very common. And so this is really the guts. It will set up the TCP listener on the designated port. It will bind one or more routers to the Blaze server, and then it will serve, which basically produces that initial stream, which is pumping events off the socket into the route. And then our main application is going to do all the the rest of the orchestration. And because we're extending IO app, this is very Haskell-like. It's just going to return an IO object. So one of the advantages of this is that nowhere in the application do we ever make an unsafe call. All we do is we construct these IO objects, and they will describe exactly what our application does. Now I'm going to end up running on Heroku, is the demo server. And to run on Heroku, you have to be able to read a port from the environment variable. So normally I would have just kind of skipped this stuff from an example, but I thought it was more valuable to have it correlate with something that was actually live. So you can give a command line argument to specify a port. If not, it'll look in the environment, and otherwise it'll just run on 8080. So ignoring that, we get to the for comprehension, and so this is quite literally our program. So when you're creating the synchronization objects, they come packaged in an IO, and so we have to extract the queue and the topic from the IO of queue and the IO of topic, and we've kind of done the naive things in both of these cases. The queue is unbounded. Typically, if you want to prevent your server from going down, you would bound the queue because you'd rather have it reject messages entirely than have it reject all the messages unintentionally. When you build a topic, you have to give the topic an initial message. I never found out why that was. I'll find out right after this talk, or maybe during it. But what I ended up doing, because I had a message that could go to a set of users, I can send a message to the empty set. And so that first message will travel through the stream, but ultimately will get filtered out from every single WebSocket. So this ends up not being particularly important for our application. And then we are going to derive the exit code from the stream expressions. And so this is really the key thing. So the primary examples have, they'll always call the Blaze server stream to get things up and going. We're going to need that, and we're going to need to always have a pull on that stream to force it to always be evaluating new messages. The keep alive ends up being important just from a Heroku perspective. So if you run this thing on a local machine, everything is fine. Heroku has an intentional feature where if there's any HTTP or WebSocket connection open for 55 seconds or more with no traffic, it'll just abort the thing. And for a chat server, it doesn't really lend itself to nice demos. So what I do instead is every 30 seconds, I'm just going to throw this keep alive message into that topic, which will get published to every single WebSocket, which will just put a little bit of activity on there. It ends up publishing an empty message that gets ignored by the client, but that'll keep all of the connections alive with that one expression. And then in terms of our application, everything we've talked about so far has all been about communications, moving messages from the socket to the queue, moving them from the topic to the socket, parsing in different directions. It hasn't really been doing any work. And this stream ends up being the entire application outside of the communications. And so we dequeue items from the queue, and then we're going to push them through our state machine, and we're going to take the results, and we're going to publish those to the topic. And the vehicle of choice that I use to move things through the queue is map accumulate. So I like to think of map accumulate as a perpetual fold. You give it an initial state, and it will take every element in the stream and apply it to that state, and then you kind of push that state forward to the next invocation. So given a chat state and an input message, we will get a new chat state, and we'll get some sequence of output messages. And we're going to produce those in a pair. And then we're just going to map down and get rid of the new state, because we're not sending that to our clients. They only care about the messages. And then we're going to lift those messages up into their own stream, and then we can push it through the topic, and that's it. And so the question then becomes, given that all of the FS2 streams are pull-based, is how do we put pull pressure on all of these things? So the WebSocket streams themselves will have a natural pull to them, but at the top level, we're going to have to pull everything, and that's where we're going to use two elements here. The one is the parallel join, and the other is drain. And so parallel join is going to take those three streams that we just talked about, and it's just going to mix them together and treat them as one. So a pull on the parallel stream will pull on all three of them as necessary. And in our case, the order doesn't matter. We just want everything to move through. We don't really care about any sort of sequencing between these three streams. We don't care about any correlation between the three streams. We just want pressure on all of them. And then what drain does is drain basically just pulls on the stream perpetually and effectively throws away the results. You don't really care about the output of the stream. We only care about the effects that it's causing as it goes through. And if, really all we care about are writes to the WebSockets going down is the big thing that we get. And then just to be kind of compliant with the type checker, we can take that unit that comes out of the drain, and we can say, hey, if you happen to get to the end of this stream, which we hope would never happen, but if you do get there, turn that unit into an exit code success, and then we'll yield that out of our for comprehension, and that's what the program will return. But we don't expect this program to ever return. So I'm going to switch to part 3 now, which is the chat state. So we looked at the WebSocket. The WebSocket is the part that's interacting with the client and just how we take things off the WebSocket and put them back on. We looked at the top level, and that's really the program execution. How do we initialize things, and how do we keep things moving through? And then we get to that one line in the map accumulate, and the question is, well, how do you do things there? And I think that this is going to be both interesting and uninteresting at the same time. It's going to be uninteresting because this is really simple stuff. This is plain Scala. We've left the world of FS2 and HTTP4S. We've left the stuff that people want to learn about, and we've entered the realm of stuff that I think probably everyone in the room already knows really well. But the reason it's interesting is that that's kind of the point of this paradigm, is that we've completely separated what the application does in terms of functionality from how it does it, from the orchestration, from the layout, from the communications. And so if I can write this process routine, which given some chat state and an input message produces the correct output, then I'm pretty much done. And I can extend this, and I can unit test this. I don't even need any exotic functionality. So I'm kind of on easy street at this point. And you can see that we'll just kind of decompose the algebraic data type of the input message, and we're just going to push things through. And a lot of the messages end up not altering the state at all. So if someone requests help, we're just going to send it to them, and we're not going to change anything. If someone sends a message to a room, which I think, let me see where that happens. right here, if someone sends a message to the room, then that's not going to alter the state either. So the only way you can really alter the state is to change somebody's room membership. And so we see when someone enters a room, we can remove them from one and we can add them to the other. And all of the routines that we're going to implement, all of our helpers, are going to return all the exact same pair. They're always going to return a new state and a list of messages. So you could send different messages to different people. You can accumulate all these things. You can imagine, if we were building like a Slack type system, we could have bots sending independent messages to different people. We could have different accumulations of things and getting spit back to people. So we can enter rooms, we can leave rooms. You can get a list of the rooms, you can get a list of the people that are in the rooms, and it's all just kind of iterating through that current state and formatting things as a string and regurgitating it out the other side. And then if we do happen to get that disconnect event, that somebody's lost their WebSocket, we're going to pull them out of the system. Ultimately, the system wasn't going to care anyway, because if you lose that WebSocket, you lose the stream. There's no real way you could attempt to push a message to a disconnected user the way you could if you were building all this on your own, where you'd write to a closed socket or something like that. Like those sorts of failures aren't really in play. But what is in play is talking to someone that's not there, is running the list command and having it say that Martin's in the room, and having my browser is closed, my machine is off, and you don't realize that. So for people's sanity, it's important to remove them. And I think that's kind of the high level thing. In the unconference tomorrow, what I've been planning on doing was taking a closer look at some of the types involved, which I think we have time for. The question is, do we have people's tolerance for that? So I'll pause for a second and see if there's intermediate questions at this point. And then we're going to check with the front table here and see if we want some comments on errors and omissions. And then maybe I'll spend a little bit looking at some of the types involved after that. All right, so we'll take a pass on the questions at this moment. How about errors and omissions, guys?
I've been working on HTTP4S for years, and I've never written a WebSocket application, so I'm learning a lot watching.
Oh, good. All right, we'll cut everything out of the video except for that. Do we want a longer break, or is there interest in taking a little closer look at some of the types involved? Types? Okay.
Who wants to break?
Well, hey, if you want to break, you can just get up and go. So that's we got that covered. So what I thought, the type that I thought was the most interesting to me in terms of just playing around, either in the REPL or I'm going to use IDEA here, just because I think it's nice to kind of line them up simultaneously and see the IntelliSense either freak out or be happy, is the pipe. So usually you're dealing with streams when you're doing HTTP4S or when you're doing like anything with FS2. Like you start with a stream and you're just kind of building on that, and it's all pretty straightforward. And then there's this other type called a pipe. And when you look at the examples, there's a lot of variance in how people deal with that. So in particular, the process input on the WebSocket builder, this is a pipe. And so we're gonna try to let me take a quick look at here. Process. Okay, so this is a pipe, and a pipe has a input type and an output type. So we'll say it's a right, of course. So here we're gonna save that guy for later. Okay. so a pipe, so we have we have the free monad, which, it's safe to always think of that as I/O, but it's not safe to write it as I/O. And so the pipe is going to be a pipe from a stream of WebSocket frames to a stream of unit. And that's what is being asked for. And so there's a lot of different ways we can write this. And this function that we've written is one of them. So it takes as an input a stream of WebSocket frames, and it outputs a stream of units. But another way we can do it is we could, another way we can write this is we could do process input 3, and I'm just going to keep carrying this forward. So we can say that that takes some, some in stream, and then we can map over the in stream, and we can just ignore the input and we can convert it to unit, and that will type check. Okay? And then similarly, we can anonymize the input argument and do the same thing. And so you'll see a lot of very different patterns. Like the pattern I saw with the least amount of frequency was writing a function. And the function kind of made the most sense to me. Like I see a lot more often, kind of this pattern in the examples. Sorry, let me just make it happy for a moment. And so it's just important to, when you see that, like that's a real clear indicator of a pipe, is that a pipe is a function that's going to externally map a stream. So you don't have the stream yet. You're going to get it at some point in the future, and you're just going to want to transform it. And so then we can take all of this other logic, and we can kind of you can put it down there. We could even build it right into this. And you see that a lot as well in the examples. And so I think that because these two arguments, they feel like they should be more or less parallel, but they're not. That is a potential cause of confusion to people. And it's also, like this was, in kind of the documents I was looking at and the examples I was looking at, pipe is simple, but it doesn't occur with much frequency. So this was the only spot that I was seeing it right here. So especially when you come across a WebSocket example and they put something anonymously right in here to go and work with that, that can be a little confusing and intimidating at first. So from a type perspective, I thought that was something that was really important. The second note that I would make from a, sorry. The second point I would make from a type perspective is that it takes a little bit of time to get your head around this stuff if you haven't worked with it before. It took me a little bit of time to kind of see the different patterns. And really the number one warning sign is if you're dealing with something that is an I/O, and in particular if you invoke like the apply function on queue or topic and you get back an I/O of something, the first thing you want to do is get that out of wherever you are and get it up to the top of your application. Like anything that when you have a kind of a single I/O object, like that's got to come all the way up to your main. You got to get that basically out of any of your handle routines. Like once you get into the stream world, if you don't have something that's a stream, you either have to lift it into a stream or you have to not have it at all. And so that's kind of a big caution for people because it's very tempting. A lot of the examples, especially things with WebSockets, they'll do things like tie the in to the out. And they'll do that through treachery by like instantiating a queue right in there that will tie the in to the out, but it only does it for that one user, and it's not necessarily what they're doing is they're not actually queuing anything in the real sense, but they are taking advantage of the fact that a queue can be used to connect two streams, and there's not really a great many ways to do that. And so that's a caution from the type perspective. So anything that starts with an I/O, if you're down in a route or you're in like the meat of your program, you want to get it out of there and you want to get it up to the top pretty quickly, I think. And then if you do see a pipe, just know that it's an external map function. And once you kind of make that connection, then I think things are pretty simple. So, questions?
Yeah, the front table is ready to do a code review finally. So lines 46 and 47, those are the ones that jump out at me. Intentionally throw a match error.
Yeah.
That's scary.
Okay.
So a couple things I can think that you could do there are if you wanted to silently handle those and not crash if that assertion is bad, you could replace that map with a collect. That
Okay.
compiles in my head. Or you could turn that into a flat map and you could log what you got that you didn't expect. I think those would be a little bit safer than being wrong and crashing the whole application. But that got me thinking. I'm suggesting things that you should do, and I'm trying to think of things that HTTP for S should do there. What messages are you trying to avoid? Is it ping and pong?
No, so when I first wrote this, everything was text-based. Like the first and if we can. If you end up looking at the project, going through the Git history is actually interesting to see the evolution of how this was kind of layered from the ground up. But in the beginning, you either are only sending WebSocket frames through the queue, or you're only sending strings. And when I got to the point of detecting that someone was disconnecting, I laid everything down to assume strings everywhere, and it was dying on a close command. And so I started handling close, and I'm like, well, I guess at this point, if it comes up with something that I wasn't expecting, I'd rather it just die so that it's in your face and you're forced to deal with it, given that I'm not trying to compete with Slack today. So that was kind of the thought, was that a fatal error I thought was desirable just because it would expose something that the example was not doing right. It wasn't interesting to me at the time that I wrote that.
So what I'm starting to wonder is there a missing intermediate sealed trait there that's just text and close? Because those are the ones that you would typically want to handle in this kind of application. And then you could be handling those and not have to, you could prove at compile time that you're not going to get those other ones.
Okay.
The fact that you had to worry about this worries me.
Well, I think it's also possible that it was a mistake for me to write. Well, maybe I don't know if it's a mistake or not. So I had the parse logic based solely on a string. I mean, I could have passed a WebSocket frame to the parse routine and dealt with it there, where there's a little more space. Like I think when you're in a route, like if your route logic expands, pretty much where it is now, where it barely fits on the screen, that feels wrong to me. And so, like at least for my mindset, I was trying to have this be compact. But if I had gotten this out into the parse routine of input message, then maybe I would have approached it differently. So I think there's a lot of different things that could be done. And I think it's reflective of, as I was building it, I wasn't really sure which parts were the most important to me. So it's.
Hey. So first of all, thank you very much. I think it's really good, and we need a lot more of these sort of practical examples. I just want to make a quick comment on pipe, because I think it's something that a lot of people get confused by.
Including me, potentially.
Because I think they think it's a lot more, that there's a lot more to it than there actually is. So pipe is literally a type synonym from a function from stream to stream. That's all there is to it. And actually, I'm not super keen on the name, because the name pipe kind of makes you believe that you're mapping every message. Whereas it's just a function, you can do whatever you want. You can take the stream, repeat it 3 times, and then do part join. And the only purpose of pipe is to make your code shorter. So there's no deep abstraction behind it. That's why you see, you said something like, oh, it's most often used with the underscore syntax. That's because the only purpose of it is to make the code shorter. So if you wanted to have the full method, then there's no point. There's no functionality that pipe gives you apart from sort of short code. So yeah, don't make too much of it. It's just
sure. Yeah. Well, so here's a question: do you think, given that this is a code example, like what do you think the best way to approach it is? Do you think it's better to be idiomatic, or is it better to be more accessible to new people?
I don't know. It's a hard question. I think I do like seeing pipe there, but it is a problem with learning. So I'm not sure with what. Okay. If I knew what the best way was, I'd try to fix it in the library so that we don't have to have this conversation. But I don't. So yeah, what do you think?
I think that it was important enough that it's part of the talk, right? Is that like being able to show what pipe really is, rather than just have code that compiles, is something that's important enough to draw attention to. Which to me means that if there is a right answer, it's going to be verbose. It would be something like having the function, and then like this first example where where you show that that function actually is the pipe or something, to be more demonstrative in the example and maybe lead people to that same conclusion. So I think that somewhere, verbosity is probably the answer, given that it's an example. But I completely agree that, I mean, when you write more and more of these things, eventually, I think everyone's going to end up inlining it right here. You're not even going to have a named pipe for the input processor.
Cool. Thank you.
Oh, goodness.
Just to elaborate on pipe, something else I wanted to add. So if you think about pipe as a type alias, right? Like in this case, a stream of F WebSocket frame to stream of F unit. Remember earlier I said like stream is covariant in all of its type parameters. But as soon as we stick those two streams, like on the input and the output side of a function, into one type, we change the variance of that F parameter, right? Because in one case it's a contravariant position, in the other case it's covariant, so we end up with an invariant type param. This led me to write a blog post saying we couldn't make Scala 2 do the type inference we wanted. And Guillaume came and said, like, oh no, your problem is this type alias. Like, if you just get rid of it, everything works. So actually the through method, which you used a lot here, used to be defined to take a pipe, but that invariance of that F type parameter caused inference to break, at least in Scala 2. Scala 3 can handle it. But anyway, and hence through is actually implemented to take a function from stream to stream, not a pipe alias. So maybe more evidence that it probably should be removed.
Any other questions not from the...
The firing squad. No more questions? Martin has a question.
Oh, I have a question. Just for the peanut gallery. So the thing that was the most interesting to me in the whole exercise was the state management. And this line here, 43, where we do the map accumulate. So a question for the front table here. When I think about, like, if I was doing this with a database, right, this line disappears and I'm replacing it with like Doobie streams or something. And the state management is completely external to my application, like the accumulation. The fact that I'm doing it in memory makes certain things easier but draws attention to this. What can you do better than line 43? And is that okay? The way it is? I mean, it seems limiting.
Quiet.
You can do state like basically sort of two different ways. When you have this sort of state which is not concurrent, right? You have put all the concurrency in the queue,
Yep.
And now you're doing what you would do with state T. You can do with those kind of methods like map accumulate or scan or all this like kind of sequential while, pretty much. And when that's not the case, then you can go back to using refs. So the stuff I showed yesterday, and go to that sort of code. And when you write that sort of code, you can easily swap an in-memory implementation that uses ref for one that just wraps a database or Dynamo or whatever. So you will have your like final tagless, store or whatever, and then you can have something that uses ref as your in-memory thing, or you just wrap Dynamo and do it that way. So when you can do this, it's cool because you kind of pushed the refy thing into Q. So Q is implemented with ref,
right. But
if you don't have that option, you can use it directly. And yeah, that's how I approach that.
Anyone else? Well, I think we all owe Martin a big round of applause. And if every single person in the room could buy him a beer, that would make me a happy man.